Welcome to the 6th week of this course. As usual, let's take a look at the PV system design overview. We started with the location-related issues, followed by the PV modules. Such design aspects lead to the fluid dynamic model, with which the DC yield of PV modules can be accurately predicted. We will now continue with the balance of system components. We already got a head start last week where we discussed the cables and batteries. This week we will focus on some balance of system components, namely the converter and the inverter. We will first look at the DC-DC converter, introducing the electrical conversion and then showing the power electronic components used for the conversion. Then we will describe different converter topologies to step up or step down the PV module voltage and their efficiency. In this video, you will learn about the importance and definition of a converter and discuss its requirements. Let's start with some basic concepts. A PV module is a voltage-driven current source, and its IV characteristics depend on environment conditions, such as the irradiance falling on the module. For each of these curves, we can identify the maximum power point. However, if the load is a simple resistor, as the one depicted in figure with a straight line, then we can see that under different irradiance conditions, the operating point may or may not overlap with the best output of the module. In this case, the solar module can only contribute a portion of the actual available power. In other words, depending on which resistance or load is attached to the PV panel, we have different operating points. Therefore, it's very important that the PV panel is always at the maximum power point of the module, and at the same time that it also delivers a maximum power to the load. The purpose of the DC-DC converter is to decouple the PV voltage from the load voltage, so that the PV panel can work at its optimum, while the load, such as an LED, a laptop, or a car, is supplied with its rated voltage. We have already seen that the maximum power point tracker controls the operating point of the modules, but it cannot set it. This task is then performed by DC-DC converter, which varies the PV voltage in order to draw always the maximum power available. Adding the maximum power point tracker is nothing else than adding an additional circuit that can be also embedded on the board of the converter. The tracker measures the current and voltage at the output side, and according to its algorithm, it sends some signals to the DC-DC converter, for example, to step up or down the voltages between input and output in order to meet the voltage requirements of both PV and the load sides. Of course, the topology can be made more complex depending on the MPPT algorithm and some other information that might be provided to the MPPT, for example, the temperature of the module and the outcome before the load. In this way, the PV power is maximized by measuring the current and voltage and simultaneously varying the DC-DC voltages. More in general, when we look at the ideal DC-DC converter, it is a dual-port component with a switch in the middle called the impedance transformer. In other words, to deliver the maximum power from the source to the load, the impedance seen by the DC-DC converter at the left part of the circuit is the same as the one seen by the load at the right part of the circuit. Now, a little bit of definitions before we move forward with the different components as well as different topologies. Here, the concept of duty cycle is described as it will come back several times. Imagine that you have a time-dependent signal, for example, a voltage that is periodic with a period Ts. It is possible to further split this period into two time spans. The first is called the T-on, and is when the signal is above 0 volts, that is when the circuit is closed. The second is called the T-off, and is when the voltage is 0, that is when the circuit is disconnected. Then the duty cycle is defined as the ratio between the T-on and the time interval, or one entire cycle. This is the principle of operation of an ideal step-down converter. We shall come back to it very soon. Here, we report other ways to write T-on and T-off as function of the duty cycle, which is the previously mentioned input signal given from the MPPT. To conclude this video, the DC-DC converter has been defined as an electronic circuit that converts a source of direct current from one voltage level to another, and the objective of an ideal converter is to draw the maximum power from the PV panel and supply it to the load. There exist three different types of converters. Buck converter that decreases the voltage of the PV side, boost converter that increases the voltage, and the buck boost, which includes both previous cases. In the next videos, we shall explain more in details these three types of converters and their components.